metabolic rate, which is the minimum calorie requirement needed to sustain life in a resting individual. So if you were in the hospital unable to move, the doctor could apply a BSA model and figure out how much energy you need to keep all your vital organs functioning. And the higher your BSA, the higher your BMR will be. In 1916, Dubois and Dubois created the first body surface area formula in the United States. They based their formula off of 9 diverse individuals, but their formula overestimates body surface area in obese people and underestimates in infants by 8%. The next equation was developed in 1935 by Boyd, and she based her equation off of 197 infants, children, and adults. 35 years later, Behan and George challenged the Dubois equation, stating that it overestimated body surface area by 15%. So they decided that they would develop their own equation and base it off of 401 direct skin surface measurement. Haycock in 1978 developed his formula from 81 individuals ranging from premature infants to adults, and his equation is most used for children weighing under 20 pounds. And lastly, Menzeler did not create his own equation. He modified the Behan and George equation, but his equation is mostly used for its simplicity, and it's been adopted by the Pharmacy and Therapeutics Committee of the Cross Cancer Institution in Canada. So these are the 5 formulas associated with the 5 researchers I just spoke of. In 1992, Dr. Wing and his colleagues assessed the 5 formulas for accuracy using the root mean squared error, and this were their ranking. And it's important to note here that each researcher only developed one equation for calculating body surface area for children and adults, where I will create 2 equations. So the assumptions I made before collecting my data is that I would exclude a subject that had a diagnosis that would affect body composition. So that could be anything as mild as a flu or anything as severe as cancer, but anything that prevented you from performing everyday activities was a cause to be excluded from this study. Also, I assumed the body to be symmetrical, and I collected data from the right side of the body. My methodology was that I collected data from 10 subjects, 5 children ranging in age from 10 to 14, and 5 adults ranging in age from 19 to 22. And my subjects were very diverse. I had an African American, Caucasian, Hispanic, and Latino subjects. I measured their height and weight in pounds and inches and converted to kilograms and centimeters and applied to the models that I previously stated. And it's important to note here that I didn't directly measure body surface area. I applied geometric calculations, which I will talk about in a second. So this slide shows the diverse range of body types. The black dots are adults and the green dots are children, and you can see the diverse range. The blue area indicates underweight, the pink area is ideal weight, the white area is marginally overweight, purple area is overweight, and the red area is obese. So I did have a child who had a BMI greater than 31.1, which is considered to be medically obese, but this child was not excluded from my study. And here's a reminder of what the BMI equation is. So as I mentioned earlier, I used geometric calculations. In 1960, Dubois and Dubois created geometric calculations that could be applied to each body segment, and the values produced from these formulas are very closely approximated with the values produced from body casting. So body casting could be making a paper mold of your arm, your hand, your leg, and then measuring that paper mold. And since that requires a lot of work, I applied these formulas. There were 19 variables and 7 equations, and I applied those 19 variables to the correct 7 equations. So, for example, your head. To measure your head, I had to measure the subject's circumference of the head around the eyebrows. B was from the bottom of the chin to the back of the head. For the hand, I measured from the palm of your hand to the tip of your middle finger. So the math I used to develop my equation is that I started out with the general form of the body surface area equation, which is constant times height to an exponent times weight to an exponent. And then I applied the natural log, and I used logarithmic properties to bring the exponential down. So it's important to note here that I also created a 3D graph, and I used data points of log BSA, log height, and log weight. And I applied a fit of plane to those data. In my plane here, I came up with a resulting plane. In the A2 and the A3 became the exponents for for my height and my weight in my equation, and I use the exponential function to make the constant for A1. So here's my resultant BSA equation for children. The 5 dots, you can only see like 4 from here, but you can see all 5 there. And those dots were the weight, the height, and the BSA, not the log. The blue surface is my body surface area equation. As you can see, it was a good fit. So then it was important for me to compare the data that was predicted from the Freeman model to the data collected from the calculations. So I used the weight and the height and predicted BSA for the Freeman model, and then I compared that with the geometric BSA. And the percent difference, which is geometric BSA minus Freeman over the geometric times 100, it ranged from negative 4.5 to 3.3. So this means that I overestimated body surface area by 3.3% and underestimated by 4.5%. This was the equation for adults, and here you can see that there's a negative exponent for weight. These are the 5 adults that I've used. The blue surface is my equation. You can see that this is a good fit as well. I also compared my data. In here, I only had a percent difference of plus or minus 1, meaning that I only under and overestimated body surface area by less than 1% and less plus or minus 1%. So as you can see here, this is one of the adults I measured had a body surface area of 1.832, and then when I used my Freeman model, only on weight and height, they also had a body surface area of 1.837. So those numbers are very close. And then this is a graph predicting all of the models. The x-axis is the geometric calculations, and the y-axis are the predicted models. So the blue dots are the Freeman model, the red is Boyd, orange is Monsteller, and I believe the pink is Dubois. And this blue line is the y equals x line. So it would be ideal that these data points would line up on the line since both axes are body surface area. The children, the graph on the right, on the left, their dots are a little bit scattered, where as adults, it was a little bit stronger, closer to the y equals x line. So overall, I concluded that my Freeman model that I produced is an excellent match to the pre-existing published models, and that the accuracy of my model produced is very accurate when applied to similar body types. Some of the references I used to help me create my model, and then lastly, I'd like to give special thanks to Dr. Shelton. Does anyone have any questions?